So example problem 4.2, we're going to go through an example of Gauss elimination. We'll start by doing by hand on the surface, just so you can see me ride along step by step like you might do by hand. Then we'll move to doing row operations collectively in MATLAB to speed that up. And then in a later example, not this particular one, it's rather short as far as Gauss problems go. In a later example, we'll be doing this through a script, through a function in MATLAB that handles everything, and you'll see it accelerates, to a computer speed. So let's go ahead and look at how to start the problem. The problem says, given a system of equations ax equals b, where a is equal to coefficient matrix of 2, -2, 1, 3, 2, -5, -1, 2, 3. So those are the coefficients. The general form would say this is x1, x2, x3. That's our array or matrix, whatever you want to call it, of unknowns. And then the output is 10, -16, and 8. There we are. So, determine the solution using the Gauss elimination method. Thankfully, this is just a 3x3 that saves us quite a few steps over 4x4, because the goal of this method is to get everything into upper triangular form. So if I can remind you, that is to make everything down here in the lower left-hand quadrant zeros through a series of row manipulations. So that will either be scaling through multiplication. No, come back. I deleted something I didn't want to. Scaling through multiplication, subtraction, or whatever other methods yeah, that's it. Either scaling or subtracting rows from one another. So don't forget to do the same operation to the solution vector that you're doing to the coefficient matrix. In fact, to make this a bit more unified, I think I'm just going to delete these unknowns in the middle so that it's very obvious we need to connect the operations from one row to another. Each row represents an algebraic equation. So the first row we seek to set to 0, or the first entry, really is this 3 in the second row, first column. So to do that, we will be scaling our pivot row, which by default we start with the first row, designated the pivot. So we need to figure out what scaling of that pivot row gives us a value 3 that we can subtract from R2. The formula we'll follow is R2 minus some constant times R1. Hopefully, at least for the second row first entry, where that 3 sits, we'll make that spot a 0. Again, we seek to make this upper triangular. So in this case, it's fairly obvious that if we multiply by 1.5, if we multiply row 1 by 1.5, that'll fulfill our needs. So row 1 multiplied by 1.5 gives us 3, -3, 1.5, and don't forget the solution would be 15. So if we carry this out piece by piece, row 2 would become, if I can write this out in a new matrix down here below, we'll just copy down row 1 directly, and the solution over here. Row 2 becomes 0 for the first entry, 5 for the second, so that would be, row 2 is 2 minus a -3, so that's essentially plus 3, makes it a 5, -6.5, and the solution vector becomes -31. For now, we could just copy down the third row, but it's handy enough to just go ahead and do the operation similarly for the third. So R3 minus some constant, it'll need to be a different constant this time, multiplied by R1. So what constant makes 2 scale down to -1? That'd be a -0.5. So this is where bookkeeping of negative signs can become a problem if you're prone to errors in that regard. So after going through these operations, you would see that row 3 now becomes, or row 1, excuse me, has become -1, +1, -0.5. And so you subtract that from row 3. So -1 minus a -1 is the same thing as saying -1 plus 1, because the two negatives multiplied together make a positive. So that would be 0 in the third row. The middle entry would become 1, so it would be 2 minus 1, 1. And then the third entry is 3 minus a -0.5, so that becomes 3.5. And the solution, of course, we can't forget that, although obviously I did up here. So that would be -0.5 times 8, would be -4 in the solution. Oh, separated on row 1. I almost made a mistake there. So negative 0.5 times 10 be negative 5. So now on row 3, solution is 8 minus a negative 5, so that becomes 13. So now this is a successful change to the first column. And thankfully, since this is just a 3 by 3, that takes us a long way towards the solution, but not quite all the way. So let's look at what we need to scale row 1 by now to make things work out. And I paused because I'm hesitant, because I'm going to intentionally step into a mistake so that you see how things fix. So if we look at these, see how we fix these things. If you look at row 3, our last objective is to make that 1 go away. So that 1 needs to disappear. If you take row 1, multiply that by a negative 0.5, you would get negative 1, positive 1, negative 0.5. So we should be able to subtract R3 minus a negative 0.5 times R1 and get a 0 in that spot. And we would with the problem that we then get a negative 1 in the first orientation. So row 3 then would become, instead of being 0, 1, and 3.5, it'd become negative 1, 0, and some other number over here. We would just undo the hard work we did to make that 3, 1 entry become 0. So that's not a viable path. This was 0, 1, 3.5. So the way we account for this is to no longer use the first row as the pivot row. We will use a row that already has a 0 in the first column location, which is the second row. So if we multiply R3 minus some constant of row 2, we'll be set up for success. So this constant in this case needs to be 0.2 because row 2 has a 5 where we need to be 1. That turns things into the final matrix of 2, negative 2, 1, 0, 5, negative 6.5. And then lastly, we get 0, 0, 4.8. And of course, I can't forget the solution vector. It's a habit of mine. My brain never remembers it, so I'll remind you several times in the video. 10, negative 31, and 13. Whoops. Need to update the 13, 19.2. Okay. Let me scoop this solution vector over a little to allow some room to write in the middle, because now we're going to use this upper triangular form and back calculate the solutions for x1, x2, and x3. Okay, to write out these formulas, we can multiply 0 times x1, looking at the third row and all the different unknowns. 0x1 plus 0x2 plus 4.8 x3 equals 19.2. Well, that's easy enough. 19.2 divided by 4.8 gives us an x3 equal to 4. So that's one of the solutions. Finished, determined, done. The fact that we know one of the variables now allows us to use equation 2, which is namely 0x1 5x2 minus 6.5x3 equals negative 31. So if we know x3 is 4, we can substitute that in, and this gives us a value x2 equals to negative 1. You have one equation, one unknown in that circumstance. So now you see how this pattern is emerging. We're going to use the first equation, which previously did have all 3 variables in it, which would have been a problem, but we know 2 of them now. So it leaves only one unknown, and that would become 2x1 minus 2x2 plus 1x3 equals 10. So we know the value of x2, we know the value of x3, leaving only x1. This works out to a value of x1 being equal to 2. So that's how you can use Gauss elimination, which basically the Gauss process stopped here once we achieved upper triangular form. Then once you're in UTF, upper triangular form, you can solve for each individual x solution progressively. You have to do them in the right order. Of course, lower triangular form has the same, I won't call it a trick, but the same simple method of figuring out what each variable is once you're done, but you start with x1 instead of at the bottom. It's just in reverse order. Use the solution given to you directly. So that's example 4.2.